Hello everyone, welcome to the second part of the presentation on areas of surfaces of revolution. We will derive now the main formula of this lecture. Let's consider a function defined on interval AB, which has a continuous derivative in that interval, and let's rotate its graph around the x-axis. The question is, what is the area of the obtained surface? Notice that the surface of a cylinder, cone, and frustum we dealt with in the previous section could be obtained in this way. To obtain those surfaces, we would have to rotate horizontal or slanted line segments. We can see that in one of our future slides, where when we rotate the blue line segment, we obtain the surface of a cylinder. In our case, however, we will be dealing with highly nonlinear functions, like the one shown here on the picture. And all we will require of our function is that it has a continuous derivative. As we look at this general surface, we see that there is no obvious way of flattening it or rolling it on a plane in such a way so that its area is preserved. In fact, it is not clear what is meant by the surface area of this highly three-dimensional surface. This is a surface which bulges outwards and inwards and wiggles its way in all three dimensions. And all we dealt with so far were, in essence, areas embedded in a plane, which could be reduced to the areas of a square, triangle, or a circle. Hence, what I would want to point out is that we are accustomed to the intuitive notion of the area, which dictates that the area of a rectangle is its width times length, but which says nothing about the area of a surface curving its way in three dimensions, like, say, a sphere. We have stumbled, therefore, into a deeper and very special kind of a problem. A problem of extending the notion of the area onto highly non-planar surfaces. We want to do it consistently so that this extension naturally coincides with the areas of the surface we already know. In case of a cylinder, we got a little bit lucky. We were able to transform those surfaces into planar objects, like a rectangle or a section of a circle, and we did the transformation in such a way that what we thought was the area of those surfaces did not change in the process. Unfortunately, in general, such transformations do not exist, and the trick which worked for a cone will not work for a sphere. Hence, to indicate that we are dealing here not only with just the problem of calculating some number, but also a conceptual definition of the area of a surface in three dimensions, I explicitly stated here what the surface of revolution of the graph of f of x is. It is a set of points with coordinates given here in blue color, where x ranges between a and b, and t ranges between 0 and 2 pi. If we kept picking x and t in these intervals, and plotted numbers, triples of numbers in a three-dimensional coordinate system according to these three formulas, we would obtain the surface of revolution of our function f. I call that surface S, capital S. Our task is to assign to S a number a sub s, which represents the planar extent of that surface, or in other words, its area. So we are in a bit of a conundrum here. The surface in question is not a rectangle, there is no height and width to multiply, nor can this surface be unrolled onto a plane. What do we do? Well, we will approximate. Let's go back to the drawing board and let's look closely at the graph of our function. Let's divide the interval AB into n equal parts by choosing points x0 through x sub n that are evenly spaced inside the interval. For convenience, we will temporarily rename the point A as x0 and point B as xn. Let the points on the graph corresponding to x's be p0, p1 through pn. By corresponding, I mean that the point, say, p1 represents the value of the function at argument x1, or in other words, p1 has coordinates x sub 1, f of x sub 1. Consider now the broken line L, which weaves its way through all the points p0, p1 through pxn. We drew that line in red color. It's clear that as we increase the number of the dividing points, the broken line approximates the original graph of the function better and better. And we can see that clearly graphically here, as the number of points inside the interval increases, so does the accuracy of the approximations. And finally, at a certain point, the red line is indistinguishable from the graph of our function. Hence, the idea is to make n very large, that is, use a large number of dividing points, and rotate the broken line L instead of the graph of our function. The question is whether rotating the broken line L instead of the graph of f will make things any easier. Let's take a look at the image on the right. It shows the surface of revolution of the broken line L. L consists of line segments whose rotation about the x-axis produces conic bands, namely frusta. We can see a typical conic band obtained in this way on the image on the right. Since we know the formula for the surface area of a conic band, we can sum up the areas of the individual bands and obtain what we would rightly call the area of revolution of the broken line L. Because L approximates the graph f of f better and better as n approaches infinity, it is natural to define the area of the surface of revolution of f as the limit of surface areas obtained by rotation of denser and denser broken lines L. This turns out to be an excellent definition. It not only allows us to extend the concept of the area to the surfaces of revolution, but also makes many of those areas readily calculable. Let's formalize the ideas from the last two slides. This will allow us to derive a general formula for the area of the surface of revolution of a given function f. We have already defined A sub s as the area of the surface of revolution of f. Let A sub L be the surface area of revolution of the approximating broken line L. The shape of L and how closely it approximates the function f depends on the number n, that is the number of subintervals into which we have divided our original interval. To make that dependence explicit, I introduced here the argument n. Let A sub f of I be the area of an individual conic band, or frustum, in the collection of frusta obtained from the individual segments of the broken line L. We can see that A sub L is the sum of surface areas of individual frusta, so we are using here the summation sign from I equal 1 to n. Using these symbols, we can compactly write the idea that we will be pursuing, namely that A sub s, the area of the surface of revolution of f, is equal to the limit of the areas of revolution of the broken lines, A sub L, and that in turn is equal to the limit of sums of surface areas of individual frusta, which were obtained by rotation of individual line segments of L. In order to calculate this limit, we need to find the areas of the individual conic bands. To make the arguments more concrete, let's work with, say, the fourth line segment P3, P4 of the broken line on our image. You can see that the radii of that conic band are the values of the functions at point x3 and x4. Hence, we can write that the area A sub F4, the surface area of the fourth frustum, is equal to pi times the slant height times the sum of the radii, but we do know what the radii are. They are namely f of x3 and f of x4, so we get the formula pi times the slant height times f of x3 plus f of x4. Let's proceed to the crux of this presentation, namely to finding the slant height of the frustum in question. The slant height L is the distance between the points P3 and P4, and we do know the coordinates of those points. Hence, we can use the formula for the distance between two points whose coordinates are known. That distance is equal to the square root of the sum of squares of differences of the points x coordinates and points y coordinates. It will help here to pull off a trick of sorts and take the factor x4 minus x3 squared out from under the square root. I place that factor outside here on the right side of the square root, and in the process the term lost its exponent too. To compensate for that maneuver, I had to divide f of x4 minus f of x3 by that term, by x4 minus x3. So I also denoted this difference, x4 minus x3, by delta x4. And I called it x4 rather than, say, delta x3, because I wanted to indicate that we are working with the fourth interval. So we can write now the formula for the surface area of the fourth frustum. It is our slant height that we have just calculated times the sum of the values of the function f at points x3 and x4 times pi. I also multiplied this whole expression by 2 and divided by 2, which is something I'm allowed always to do. And as a result, I can now deal with the average of the values of the function f at points x3 and x4. And that's the red term here. And I also highlighted in blue another term that we will have to focus in a moment, namely the average rate of change of function f on the interval x3 and x4. In order to make progress on these two terms, which turn out to be key terms in this formula, we will have to use two theorems that we already know. So for now, let's hide the results of our calculations under the hat, and let's proceed to the two theorems. Okay, the first theorem, the intermediate value theorem, states that whenever we have a value y between the endpoint values of a certain continuous function on an interval ab, so whenever we have that value y, there always is a certain argument x circle within this interval such that the value of f on x circle is y. We can visualize this theorem here on the top picture, namely as we range with y between f of a and f of b, we can graphically always find the x circle inside the interval ab such that where our function f takes the value y. Okay, so in the previous slide we were considering the average of the values of f at points x3 and x4, and that's the average. Now, since the average is always between the original values, the intermediate value theorem tells us that there is an internal point x sub 4 circle where f takes that intermediate value. Hence, we have obtained a very nice simplification of this red fraction. Okay, so let's now proceed to the mean value theorem. The mean value theorem states that whenever we have a function which has a continuous derivative in the interval ab, then its average rate of change, represented by this fraction, is equal to the derivative of this function at a certain internal point x star. So we can visualize this theorem on the picture on the bottom here. Namely, the average rate of change of function f is equal to the slope of this secant line, which is built on the endpoint values of function f. Now, the derivative of function f at a certain point x star is equal to the slope of the tangent line to the graph of the function at point x star. So as we range with x star between points A and B, we see that at certain point x star, we have that the slopes of both lines, the tangent and the secant, are the same, and that's the point whose existence is claimed in the mean value theorem. So what that means is that we can look at this blue expression, which is the rate of change of the function f on the interval x3 and x4, and we can replace it by the value of f prime at a certain internal point. Okay, we can return to our calculations, namely to the expression we have left under the hat. We can now replace the red and blue terms by the values of the function f and its derivative at some points inside the interval x3, x4. And that's what we have done here. Hence, we have obtained an expression for the surface area of the fourth frustum in terms of the values of function f and its derivative. In general, one can see that the arguments that we use to work with the fourth frustum would be exactly the same for any other interval, for any other frustum. So effectively, we have obtained an expression for the ith frustum. And I have this formula enclosed here in this blue box. One note that the internal point, the interval here listed is x sub I minus 1 to x sub I, and the internal points in that interval are x sub I circle and x sub I star. And again, I denoted by delta xi the difference between the endpoints of that interval, or basically the length of that interval. So now we know that the area of the surface of revolution of our broken line L is simply the sum of all the frusta, which translates into the sum of all these expressions over all I from 1 to n. So that's what I wrote here. Now, in order to make progress, we have to make one approximation. Namely, we can replace, it turns out, the internal points x sub I circle and x sub I star with the midpoint inside this interval. It turns out that although the expression that we're gonna get is not literally the same, but the limits of both these expressions on both sides of this approximately equal signs are the same. And those limits are the same only when the involved function, our original function, has a continuous derivative on the whole interval from a to b. Otherwise, all bets off. We could not claim the equality of the limits here when n approaches infinity. Now, why did we do this? And I can quite understand that some of you could now despair that we have been digging and digging, and there's no light at the end of the tunnel inside. Wait there is good news. We're almost done. The sum in the orange box is the Riemann sum of a certain function. If you recall, one way of defining Riemann sums is to divide the interval into a number of equal subintervals. And that's what we've done. Then one needs to sample the values of the function in each of those intervals. And that's why we took the midpoints. And then multiply those values by the length of the interval where the value was taken from. But that's what we have here. Delta x sub I is the length of the ith interval. In our case, those intervals are the same, have the same length. So we certainly, in the orange box, have a Riemann sum of a certain function. It is not the function f of x as we perhaps would like. It is a Riemann sum of a certain more complex function, but that function is still manageable. Namely, it is f of x times square root of 1 plus f prime x squared. I have written here in symbols what I have just said. The area of the surface of revolution of the broken line L is approximately equal to a certain Riemann sum. It is a Riemann sum not of perhaps function f of x as we would like, but of a slightly complicated but still manageable function f of x times square root of 1 plus f prime of x squared. So we can say that the limit when now, one important observation, this approximation becomes equality when n approaches infinity. We can say, therefore, that the limit when n approaches infinity of the areas of the surfaces of revolution of the broken lines L is equal to the limit when n approaches infinity of certain Riemann sums. Now, as we know by definition, Riemann sums converge to the integrals of the involved functions on the involved interval. Therefore, we are basically able to calculate the limit on the left. It is equal to the integral that we see here on the right. Now, this limit was taken to be the definition of the area of the surface of revolution of our original function f. So we can say that a sub s, the area of the surface of revolution of function f, is equal to this particular integral. So we have completed this long journey, and we will use this integral formula in the next section, where we will apply it to the surface area of a sphere, and we will prove a remarkable theorem by Archimedes about a sphere and its circumscribing cylinder. Thank you for listening.